I'd like to kind of give you an overview of what is the AI capability at StatsBomb, because this is actually quite critical and important to everything we do. And making sure that we have a proper foundation to be able to do what we want to do is really key to be able to generate things in good time and be able to scale them up to different sports, different sort of, features, etc. So we spend quite a lot of time and effort making sure that our AI infrastructure is modular and scalable, allows us to interact with other teams within StatsBomb to be able to ship these sort of models and products across the board to different front-end teams, especially in the collection process, so we can actually generate the data that you all use and love. It's actually quite important for us to make sure that these processes are in place. So when we actually apply AI on one particular sport, we can also apply it to another one without necessarily having to reinvent the wheel again from scratch. And this is to our strength, really, because all of our AI technology is sort of sport agnostic and allows us to scale from American football, which what we call here AMF, or soccer, which is real football. But this is the sort of where we actually are, and trying to develop these capabilities so we can across not only on these sports but other sports as well in the future. So, as we said, scanning. I think throughout the day I've been talking to a lot of people, and a lot of people come in asking me about the title of this, and I already see a lot of interest of being able to quantify scanning. I think scanning could potentially be an interesting feature in our database that allows us to do a lot more. It helps us a lot to understand about the situational awareness of a player and a team, and also help us understand, for example, some of their decisions, and potentially can actually feed into models that will probably improve accuracies in predicting certain sort of metrics or scores. However, scanning is a very good example of why we need automations and AI. It's almost impossible, or not even scalable, for anybody to be able to generate scanning data without necessarily having some level of automation. Because if you're going to task any sort of sport expert or collectors to be able to look at the video footage and try to quantify where players are doing, it's an enormous task, for a single player, let alone for an entire team, two teams, across a match, across a season, across a league, multiple years. That's enormous. So really the way forward for this to happen is to have a good level of automation. And that's really the key here. So what we're doing here, and it's not only my work, I'm being mainly a spectator. My team did most of the work, if not all of it. So I'll make sure that their credit as well is clear here. But the key here is make sure that this sort of technique that we've been working on is kind of a proof of concept to demonstrate the feasibility of automation in scanning. And another thing about scanning is, it requires quite a lot of stuff in there. So it's not really simply developing a model and applying it on a computer vision footage or whatever. You're going to have a lot of steps along the way in order to get to a position where you can even quantify scanning. You have to detect the players, there's a long list of things that you have to do before you even get to the position where you can actually quantify it. So these are the steps. Obviously you need to detect the player, that's obvious. I'm sure a lot of you already seen a lot of different sort of object detection models. It's all over the place when it comes to AI machine learning. But there are certain things about what we do in StatsBomb that makes it more customizable to our stuff, and I'll talk about this a little bit later. The other thing is homography estimation. What I mean by this is when we detect a player, we want to also detect their position, not in the video footage or the frame, but on the actual pitch. So this is what you've probably seen already in our StatsBomb data. When you have a pitch and the position of the player, this is being mapped automatically from the video footage to the real coordinates on that particular pitch. And that is tricky, obviously, because different sports, different sort of venues will have different sort of mark, and characteristics that will make it sort of, different. So we have to adjust the model to allow for that sort of difference to be able to predict accurately the dimension of the pitch and the mapping between the frame to the pitch, etc. The next thing is player tracking, and that's important because the information tends to be across a video footage which basically spans a period of time. It's not only on a frame. So being able to relate metrics from one frame to the other is going to be crucial for us to be able to aggregate this over time. And in order to do that, we have to know association across multiple frames. And now we're getting into the gaze or the gaze estimation or the scanning bit. We have to estimate the posture. So each player, we need to know how they're standing, some key points or key landmarks of their body parts and how they're positioned, and being able to use that information in order to deterministically compute the scanning or where they're looking and estimate the direction of gaze. So that is basically the process. In production, which is not really happening this at the moment, it's just a proof of concept. This will have to pass also through our human collection process, where we do the quality assurance, we would do enriching the data, tie it up to event data, etc., and obviously making sure that the AI errors are being corrected and all of that good stuff. So I will probably talk a little bit more about initially about the player detection and the homography estimation, and just mainly to talk about, how we do this on a very high level. Some of you might have already been familiar with some of these techniques that we use, but it's based on something called Detectron, which is an object detection framework that uses convolutional neural network under the bonnet, if you like. And it's a very established framework. It has been proven across different applications, different domains. We took it and optimized it to our own need using something called transfer learning, which is basically making sure that this model is more equipped to deal with our kind of data, which is the sport data, if you like. And the outcome of this basically is bounding boxes. That's all it is. Bounding boxes of players across the field. And it's important to note here as well is that we care about obviously detecting the position of the referees and all of that, and the spectators around the field. You don't want to mix these with players automatically in order to reduce the amount of time the human collectors and actually spend on correcting the outcome of the AI. And this is like the sort of things this is like an image from an American football sort of pitch. And you can see here detecting the players, nothing really special about it. But once we've done that, we also apply an end-to-end novel sort of homography estimation model that we built in-house in order to locate these players from a frame to a real-life coordinates, if you like. And this is an example in football as well. Right, so now talking about tracking. Tracking is, as I said, is a well-established problem. It has quite a lot of different diverse applications. It's been around for ages. And we've done a lot of work in this area in order to understand what is the best solution. We have a system that is working based on the deep sort model. If you want to know a little bit more about it, feel free to ask Johan. He's sitting here. He's built most of it. So that is basically sort of, building on existing work and optimizing it to work to do our bidding, if you like, in our data. And the whole algorithm is re-implemented in-house, so we actually have control of every single aspect of it. It has been proving to work actually very well in a lot of different type of data. But also one special sort of nice feature about it is it allows us as well to have something called embeddings, which gives us the possibility to be able to associate players with each other in a frame if they sort of have been occluded. So if players cross each other or tackle each other, if you just use the physics by itself, these things could be mangled and sort of confused. But if you use sort of appearance model, then you can actually resolve that confusion and make it better and actually predict a much better track for each player. And just to make a clear note here, at this point, this is going to be an anonymous track. So it would give that particular player, doesn't know the player or the player identity. It knows that this player A or B or whatever, and later on in the enrichment process, that player identity will be associated to them using that track. So this is an example here showing how tracking works in two different sports. And just to be clear, nothing here has actually been changed other than the input data. And this is basically non-filtered. This is the outcome, the raw outcome, if you like. It's just showing the position of the player after being detected and tracked on the real page, and basically is trying to estimate their identity or track ID that become associated later with a real identity. And it looks quite cool. I like the kind of the maps. It looks like a game of some sort. So now going into posture estimation. Posture estimation is actually quite interesting, especially in this sort of application. It makes it really hard because, when we want to actually predict the posture of somebody, we tend to have a very close-up of the human being, where we can see clearly their body parts and how they're standing, etc., which makes it a lot easier. But when you look at, for example, sort of broadcast footage, it's really difficult to kind of see, and there's not a lot of pixels for each player to know where, for example, their sort of, shoulders are, eyes, ears, things like that. Sometimes these are actually not even in the view because they're turning their head or whatever. So it's a very challenging problem. And this is kind of where the scanning stuff really heavily relies on. If we can actually solve that problem, then that gives us a lot of hope to be able to solve the problem with detecting and estimating the scanning correctly. So we went through an exploratory process, and we actually came across this sort of model, which is called the HRNet, which is basically looking into multi-layered resolutions of different sort of hierarchical sort of convolution neural nets that feeds into each other. And the key here is that they feed into each other from different resolutions. This is very important because it allows us to be able to home in onto the small landmarks from a very far away, zoomed out sort of picture where we only have few pixels. But that by itself wasn't enough. So there's something called the dark model, which is basically distribution-aware coordinate representation of key points that allows us to kind of improve that by modulating the heat map outcome of the landmark prediction and then applying some sort of Gaussian modeling in order to be able to find a maxima which is a lot more stable than what we get naturally from the model itself. And that seems to be actually working quite well. Even with things like this, where you're actually quite zoomed out, you can still see people sort of body posture landmark quite clearly detected across all the players. So once we've done that, I know it's a long process, but once we've done that, we actually now have the ability to be able to start computing gaze, or the direction of where people are looking. And it's actually a simple process. Up to this point, it's a lot easier to actually then sort of deterministically sort of compute that because you've got all the components you need in order to do that. So the first step would be, for example, identifying certain sort of landmarks, like, eyes, ears, shoulders, whatever, that we can use in order to compute a plane and then find the norm against that plane in order to estimate where the player is looking. Once we've done that, then we can use the tracking in order to allow us to feed in information, temporal information from other frames, which could be quite helpful because it gives us a little bit more stability, gives us a chance to kind of improve the prediction as well. And once we've done that, we can then quantify the position of where the players are looking, oriented their head, actually using this radial histograms. And these radial histograms are actually really quite simple. And what they are basically is the number of seconds in that particular video clip each player has been looking at, basically. And I can show you this in a moment. So this is an example of Iniesta. He's doing a very nice sort of fade action there. And this is a zoomed in sort of video, mainly for demonstration, because it's a lot easier to spot where their eyes, their head, all of that with a zoomed in picture. But generally speaking, it's very rare to get this sort of footage in a normal setup. And we want to optimize our processes to work with broadcast because this is where we feel the most value will come, the scalability from existing data. So again, this is what happens. So you can see here, we've done this, all the stuff that we've done before. And as this happens, the histogram has been generated for that particular clip. And it tells you with number of seconds how long in each direction he's been looking at. And this is kind of the outcome. I mean, the histogram is really down to us, to how we actually present it. Up to this point, once we actually get this data, it becomes quite easy to customize this in terms of frequency presentation, even like a singular metric that groups that if you want to. And this is another example. You can see here, it's still a proof of concept, but it's pretty decent. I think we can do a lot more. Can we improve it a lot more? But I think this, as a proof of concept, it looks pretty good. And here, this is ultimately what needs to happen, basically. So you can see here, this has been sort of done automatically. There's no human intervention there on all the players in the scene. You can see some jitter and things like this. Again, it's still a proof of concept. I'm sure we could do a lot better than this. We only spent like maybe a few weeks on this. And once we've done this, we can generate things like this for each game, and that is basically down to us really to decide how the data would look, because we got all of this data, how to quantify it, how to present it, how to put it up there for people to use. We're very happy to hear sort of feedback and requests and demands and how people think this particular feature might be helpful to them in the future as well. But this is the sort of things we can actually see. And this has been sort of done on a player-by-player basis on that particular game, on a particular segment. You can do it for an entire game or some part of a game or play that you are interested in. So that's kind of where we are at the moment. Obviously, there's a lot of work to be done, but we wanted to share this with you, kind of work in progress, if you like. We have used like off-the-shelf, for example, like posture estimation models. We can do a lot more using our own data. So we have we are really, really fortunate to work with our colleagues and friends in Cairo who collect a lot of data for us. Some of them are sitting here. We're very grateful because that data sort of sets us apart, helping us build our models and make it better in so many different ways. So we can use that data in order to train much better models, to customize them for certain sports, etc. We also can use a lot more information from the posture estimation we generate. We only use a small fraction just to demonstrate the concept, but we can do it with a lot more, and that will certainly improve the accuracy and the performance. And as you can imagine, that could be quite applicable in all sorts of different things. This is just listing some random ideas of how this could potentially be used. But you could potentially, for example, actually sort of quantify all the players in the team or where they're looking at and map this to the pitch, so you would see which part of the pitch is being covered in terms of gaze of all the players, and almost have like a heat map which part of like blind spots in the entire pitch as well. There's a lot of stuff you can do. You can add, for example, to the OBD model to the XG model. You can have it as a separate metric that potentially can help you for scouting. All sort of different application potentially could be useful for that. Right, I think that's it. And again, I'd like to thank my team. I'm very grateful to have this team. They've been working very hard, not only on this, and a lot of other things at StatsBomb. So I'd like to Alistair, he's been an intern with us for a few months, but he's done great work. Javier, Johan sitting here, Miguel, Iñaki, Craig. So we've been working very hard to generate this sort of AI tools that help our collection processes and produce things like that. Thanks very much.
Okay, very interesting, and you clearly are showing very well how the player move their head. You are talking about gaze and looking. That's really not the fact that we can track how the player is moving his head doesn't say where they are looking. Where they are looking is basically either in central vision, when their eyes are pointing in this situation, or when they use their peripheral awareness. And in football, peripheral awareness is as important as central vision. The other thing is that when they move their head very fast, they are not seeing anything because the brain switches off, otherwise we would see double. So fantastic work on head movement, but that's really not telling us where the player is looking at any time.
Yeah, fair enough. I think what we potentially could do, as you said, this could be an initial indication that we could. So we're not only tracking the head movement, we're actually looking at the eye's position as well. I take it that obviously people will move their pupils without moving their heads. That's absolutely fine. But as an approximation, I think this is the closest you probably can get other than having somebody wearing a tracker on their eyes. So from broadcast footage, I think it's probably the closest we can get to scanning in that sense.
Hi, I would like to ask if this has been implemented or experimented with any club, or have you received any feedbacks from the players or the coaches regarding this technology?
This is the first time anybody sees this. So it's just purely a proof of concept, a feasibility study to see if this is possible before we actually embark on doing it at all. So once we actually gauge the reaction, whether it's going to be useful to people, it might not be useful as well. Like, we don't know. But we want to do something that is useful to the community. We just don't want to create another column in the database that just shove it and people just face and just, okay, here you go. We want to create something useful. So depending on the feedback, all of that input and sort of discussions will really help us shape how that feature might appear in our database, if at all.
Did you try the scanning for American football as well, or is it only for soccer so far?
At the moment, it's on the soccer, but it's actually mainly because the conference is mainly soccer-oriented, but the technology is sport agnostic. It is something on our actually roadmap to try it out on American football because we currently working mainly with American football as well. So it's something definitely on our radar at the moment. Obviously, in American football, we have an extra complication where people wearing sort of helmets and stuff, which make things a lot more hard, difficult. But it is something that we would like to try and see how that works as well there.
Thank you for an incredible presentation. I was wondering, maybe you said it, but how long has it taken you to develop what you've just shown us?
So that's what I was trying to say earlier. We've actually spent a considerable amount of effort to sort of kind of build our AI infrastructure at StatsBomb. We're using the sort of cutting edge technology in terms of ML ops and sort of computer vision, machine learning stuff. So this work in reality took us about maybe 4 weeks to generate, but mainly because we're standing on a shoulder of a giant basically. All of the infrastructure beneath us, allows us to move very rapidly, do things like this very quickly. But the amount of work we're going to start doing from zero is going to take you much, much, much longer.